Hi. Yeah, if you mean like this problem, you just do BFS on it. Okay, so since the division 2 problems, it seems like pretty much everyone solved them this time, so I don't think I have to go over these two problems. And I'll just put the code here just in case anyone wants. Yeah, I'm just going to go over the first few div 1 problems first, because like the division 2 problems also share some of the problems with division 1s, the first 3 problems. So we're going to start with under the tunnels. Okay, so if you see the input, you're basically given this matrix of ones and zeros. And this is actually very similar to an adjacency matrix. So what we do is you can look at this matrix, which is S of I and J, and we create an edge, and it has to be a directed one from I to J if in the matrix row I and column J is equal to 1, and also because we have this condition here where I and J, the difference between I and J has to be smaller than or equal to K. So you also need this condition. And once we create this directed graph, we can simply run BFS on this graph to find the shortest path from 1 to n. So that's pretty much it for this problem. And I'll put my submission here. And then if nobody has any questions for this problem, then I'm going to move on. So in order to learn graph theory, you can filter problems by tags on like Codeforces and CodeChef. The third problem. Okay, if nobody has any questions, then I'll move on to construct array. Okay, so for construct array, basically we need to count the number of arrays which satisfy this condition that no 3 consecutive elements are equal. So, and the constraints are very large for this. So since this is a counting column, it means that since this is a counting problem, it means that we should probably try some dynamic programming solution. So actually, a dynamic programming solution works. So let's see the number of sequences of length I. Then you know that dp1 is equal to n, and then dp of 2 is m squared, and dp of 3 is m cubed minus m. And you have to subtract m because there's a case where there are the arrays. You have to consider the arrays which have all elements equal, like this, for example. So we need to subtract these arrays. So what about the general case where I is greater than 3? Well then, first we can, if we have an array of length I minus 1, then we have m choices for the next element. So we can start by saying dp of I is equal to m times dp of I minus 1. But then you have to consider the arrays that could be bad. So maybe there's a case that we chose x for this new element, but then the last two elements of the array of this prefix is also x. So this will be bad. And we want to subtract the bad cases. So it turns out that for the bad cases, it turns out that all bad cases start with a prefix of length I minus 3 of any good array. Then we have this suffix of length 3, which has all elements, which has 3 elements that are equal. So we have m choices for x. We have m choices for the element that we choose to have to occur 3 times in the suffix. So you know that the number of bad subarrays is m times dp of I minus 3. Wait, actually, then there's the case where there's also the case where the last element of our prefix is also x. And then, so maybe like our constructed array looks like this. And this type of array is not counted in the good arrays that we created from this. Because if the last element of this prefix is the same as all of the elements of the suffix, then it means that like this prefix of length I minus 1 is bad. So actually, we need to make sure that if this is y, then y is not equal to x. So in fact, instead of m choices, we can only have m minus 1 choices. So this is our DP recurrence for finding the answer to this problem. And then we can, but because n can be up to 10 to the 18, we need to use matrix exponentiation to calculate the DP. So I'll just include a link here. if you haven't seen it before. Now also include my code for this problem. Oh, my matrix is actually 3 by 3, but the 2 by 2 matrix seems interesting. But anyways, I don't think it's too bad. So if nobody has questions, I'll move on to the next problem. Okay, then for this problem, okay, so we're given a piece of paper, and you have m points on this piece of paper. And one thing we can do is we can just go through the string in reverse order and then try to basically try to expand the points. So for example, if we see that the last character in the string is L, so we try to duplicate the elements to the left. So this point goes over here, this point goes over here, this goes over here, this point goes over here, this point goes over here. And basically, after we process the last character L, we move on to D, and then we can do the same thing and we duplicate the points again. But then if we do this process too many times, then we'll eventually end up with too many points. So one important observation is that the total number of L and R operations we need is 2. And then this is the same for U and D as well. And this is true because if you take the paper and then you copy it many times, then a lot of the things you basically only need to find the nearest pair of points, and a lot of the points are already duplicated a lot of times. So if we copy them more times, then it won't be helpful. For example, if we have a point here, AB, then if we try to copy this entire thing over, then we'll still get the same distance between A and B. And also for 2 points, like if you have A and B over here, you realize that you can figure out that A and B actually already appear here and here. So there's no point in copying the paper again. So if we only do 2 number of times for L and R and 2 times for U and D, that means that we end up with, at most, we start out with n points, so we end up with at most 2 to the power of 4 points in the end. Okay, so looking at the constraints of n, this is around 16,000. So after we find all of the points, what we can do is we can finding the nearest pair of points in a set of points is a standard problem, and we can just copy the code from a website, and this is the website that I use. So you just copy the code for this, and then yeah, you can get a C for this problem. And I'll also include my code. So are there any questions for this problem? Okay, then we're going to move on to the next problem, which is minimum and maximum. So in this problem, okay, so this is an interactive problem, and we need to find the indices of the 2 smallest and 2 largest elements in it. Wait a second, I need to change the status. Okay. So let's just focus on the subproblem where you only have to find like the 1 minimum and 1 maximum. So then what we can do is, if we have an array such as, if we have an array with some random values, we can pair the values up, and then we'll do a query for all of these values. Then in total, we'll use up n divided by 2 queries in this step. Afterwards, we'll find the minimum and the maximum of each pair. And after we do that, we can kind of arrange these pairs in a segment tree. Like we can arrange these pairs like we make these pairs the leaves in a segment tree, and then we cursively find the minimum and maximum of each of these segments. So for this leaf, the minimum is 4, the maximum is 7. The minimum for this leaf, the minimum is 3, the maximum is 8. And then for this segment, you can find that the minimum is 3 and the maximum is 8. And we do this for all segments. And we do 2 queries for each segment in order to find, we use 1 query to find which segment has the minimum, and we use 1 query to find which segment has the maximum. So for each internal segment, we use 2 queries. So the number of internal segments is about n divided by 4. So which means that to find one minimum and one maximum, we use around 3n over 2 queries. So now we just need to find, our next problem is to find the second minimum. So the way we can do this is so first we notice that in order to find the first minimum and the first maximum, we already used 3n over 2 queries, and the limit is 3n over 2 plus 20, which means we can't use too many queries to find the second minimum and the second maximum. And it seems like since n is less than 1,000, it seems like we can use about log n queries to find the second minimum and log n queries to find the second maximum. And this is also why we use the segment tree structure here. So in this example, I'll only do this for the minimum. So for this entire array, we find that the minimum is equal to 1. In order to find the second minimum, let's delete this 1 from the array. So then we can update this 1 with the 2 over here. Actually first we delete the 1 over here so that the minimum becomes 5. And then since we also need to update this, and then we need to find which one of these is the minimum, which we can use a query to find that, and we find that it's 2. And then we move on to the parent, and we need to find the updated minimum, and which is 2. So if in this example we find that the second minimum is equal to 2, the value of the second minimum is equal to 2, then we can do pretty much the same thing for the second maximum. And so our final query count is about 3n over 2 plus 2 times log base 2 of n. And I'm going to paste my code here. Okay, so my milestones. So the 50 points was because I didn't implement my segment tree correctly. So for example, if I had an array of length 6, then you should pair the elements like this, but instead I divided the elements like this, then I paired them like this, and then I had 2 of these elements left over. And then so basically you're supposed to pair as many elements together as you can to save queries, but then I didn't do that in my first few solutions. So that's why. To cover the theory part of CP, you can really do problems from anywhere, and then if you can't solve a problem, then you can look at the solution and see what theory is required in that problem, and then you learn it that way. So basically you should do problems first and not learn theory. So if there are no more problems, if there are no more questions, then I'll move on to the last problem. Okay. Okay, so the first thing, so basically we're given this string and then we don't want any of the ones to be adjacent. And then what we can do is we can swap any two adjacent elements for a cost of 1. And we want to minimize the number of swaps. So the first thing we can do is, instead of having a string like this, we can store the actual positions of the ones in the string. So for this test case over here, 0, 1, 1, we'll change it into a vector with positions 1 and 2. So this is 0, this is 1, and this is 2. And then the second thing we can do is you want to make sure, let's call this array P, and you want to make sure that in our final array, Pi is smaller than or equal to Pi plus 1 minus 2. So instead we can simplify this condition by taking our array P, and we take our array P and we minus 0 for the first element, we minus 2 for the second element, we minus 4 for the third, minus 6 for the fourth element, and so on. So this array P becomes, because after our transformation, P becomes equal to 1 and 0. Then our condition over here becomes P of I has to be smaller than or equal to P of I plus 1. And this is easier to deal with because we don't have the constant value over here. Okay, so next thing is that in our problem transformation like this, we didn't consider the fact that we want the original. So for all original P of I, you have to make sure that P of I is within this range. But then if we transform our P to the new problem here, then we can't guarantee that. So what we should do is we need to add, so before we do anything with the string, we should add 2 zeros before and after it, and then we add a 1 before and after the zeros. But these two ones should have a weight of infinity, so then they can't be moved at all. So this is how we can make sure that the ones in this array don't move out of the limits. Okay, so our new problem is we have so actually given p can, in one operation, you can add 1 to p or subtract 1 from p. Then we need to make sure that the final array satisfies that the final array p has to be non-decreasing. And then also the cost is just the sum of ci times w, the weight of I. And the weight of I is 1 for all of the normal elements and infinity for the elements for the element that we created in the back and in the front. And C of I is equal to number of operations we performed on P of I. Okay, so now we have simplified this problem by quite a bit, and we can consider one of the subtasks here. So it says the sum of n overall test cases does not exceed 5,000, so we can use an quadratic solution. So one solution we can use is dpix, which is the minimum cost for prefix of length I, and also the last element in this prefix is equal to x. Then if you can do this, you can write this dp pretty easily in quadratic time, and that's how you get the 50 points for subtask 1. But however, for the full solution, we're going to need to a few optimizations. So actually, you can I claim that dp of I is a piecewise linear function. So what I mean by that is that dp of I and also dp of I is convex. So it starts like this, and then and all segments are linear. Then maybe it ends up like this. So basically dpi, you can model it as segments of lines connected together, and they are convex. Then you can prove this by using induction. So the way we transform dpi to dpi plus 1 is basically we take dpi plus 1j is the minimum of dp I of k, where k has to be smaller than or equal to j. So if you consider this graph over here, just copy it over. This is our dpi. Oh wait, I forgot to. And also you need to add the absolute value of j minus p of I plus 1 to the end. Okay, so this part So actually this graph is dpi of x. And then in order to make it like this graph, what we do is we can actually remove the parts of this graph which are increasing. Remove this, and then this just extends all the way. And like as x becomes bigger, the function just becomes constant. And then this new graph here looks like what we need in our dp. Looks like the expression in our dp. So now we can also draw this graph here. So if this is p of I plus 1, then we know that the graph looks like this. And then what we do is we simply just add these two graphs. We add these two functions together, and then we can create the new dp of I plus 1. And the way you do that is for each function, we store a set of slope changes. And then, so what I mean by set of slope changes is the places where the slope change. So for example, for the first function here, one place where the slope change is this. And for the second function here, the place where this function's slope changes is over here. So, and then in order to add these two functions together, we can add their y-intercept together, and we can also and then we combine their two sets together. And that's how you get the new function. So after all of this, we can calculate the final dp, and our final dp will also be a linear piecewise function that's convex, and then we can just iterate over all the points where the slope changes and find the value, and then we find the place with the minimum y value, and then that will be our answer. And in fact, this dp is known as the slope trick. So yeah, here. So this blog actually has a lot more, describes the slope trick in a lot more detail, and also has a lot more problems, with a lot more harder problems than this one. So if you're interested, then you can go see it. And that's basically it for this problem. So I'll see if there are any questions that people have. Okay, I'll start from the top. What? I'm not. And I didn't solve all of the slope trick problems, but I've solved like several of them. So several of the important ones. And this is a pretty, yeah, this problem is one of the simpler ones among the ones on the blog. So yeah, it wasn't too bad. Oh, okay, I see. Oh yeah, you need to do the pairing process first in order to get it to be 3n over 2. Okay, so what do you mean by using dp to check every possible move? Okay, so I don't exactly know how that formula is supposed to work. Virtuals are good for like just getting familiar with contest environments. So like I guess you learn how to like work under time pressure, but it's not as good as doing the contest in real time. Oh, I see. Yeah, so for example, for the array, like with 4 ones like this, you will subtract this array like 2 times in your formula. You subtract it once when, so your n minus 2 here is for the starting position of the subarray of length 3. So for this array of length 4, like there are 2 possible starting positions. You can either start at this element or you can also start at this element. And so this array, which is bad, will be subtracted from the total count like 2 times, which is why the formula doesn't work. Okay, so in the problem under the tunnels, like we can jump both forwards and backwards. So it ends up that there can be cycles in the graph, so dp doesn't really work for this problem. Okay, so nobody has any more last questions, then I'm going to go off. So resources and links where beginners can get a start. Really, you just need to know the important online judges like Codeforces, CodeChef, AdCoder, and just need to do problems on there. And if you don't know something in a problem, then you just need to search it on Google. And there are a lot of resources on Google that you can find. And yeah. So DP might not give the minimum with cycles. Like, because usually when you do DP, like, you don't have cycles. So if you do have cycles, then you should just use a pathfinding algorithm like breadth first search or Dijkstra. And also, to answer your question, I just basically learned all of the data structures and algorithms by searching them on Google. Yeah, yeah, it's really just that simple. And for 1 second versus 2 second, there's not much of a difference, I think. Not exactly sure. Not exactly sure if it's my side. Like, if other people don't seem to have the same problem, so I think it's fine. And then I don't know, well, I do know a few good books. I've heard of books in competitive programming, but I don't really know if they're good or not, because I haven't used any books for CP before. I basically just search everything that I need online. Beating Gennady is too hard, and I'll never be able to do it in 10 years, probably. How to spend time efficiently on contests like IOI. I kind of don't know how to spend time efficiently. Like, if I did know, then I think I would have done better last year at IOI. But I think I think everyone needs to find their own strategy, and to do that, you need to do a lot of virtual contests. So, yeah, so you should probably just practice a lot of past Olympiads and see what strategy works for you. And I kind of used to do math contests. Yeah, so when I got into competitive programming, I knew most of this math that I needed. So yeah, UCycle training pages are outdated, and so I think use more recent online judges like Codeforces. Yeah, how do you spend time efficiently? I only got a silver, so you should teach me your strategy. I don't have any plans to upload video lectures yet. Yeah, I have seen Benjamin's math counts episode. I actually went to math counts before, but I'm not as good as him, so I didn't get into the final countdown round. You don't really know what I would if I were to collaborate with Erich too. I don't really know how to yeah, I don't really know what I would do with him, like what we would do together. I'd probably so I would probably start from the higher bits and see, and I'll check if a pair exists with the highest bit. And if it does, then I'll make sure in the answer includes the highest bit. And if it doesn't, then I'll just move on to the next bit. And my setup is not really anything much. It's really just it's really just yes, I basically just use Vim, and I have a Vim RC file. And this is basically what I use. So I'll just paste it here if you want to see it. And then, okay, so for your question, how to balance between competitive programming and a girlfriend, you shouldn't be. I'm not the person to ask for this because I'm probably I don't think I can get a girlfriend in like 10 years. So, yeah, I'm the last person you should be asking about this. I'm not being humble, I'm just being realistic. Like, it's actually a fact that competitive programmers have a very low chance of getting of having good relationships. Okay, so if there are no more serious questions, then I'm going to go off and edit this video and make it public.